Yeah, thank you very much for this very kind introduction. Also, thank you very much for even inviting me, and for organizing this whole workshop. It's great. Also, thanks to the previous speakers. I'm really enjoying myself here. It's great. Yeah, so today I have the task to give you an introduction to evolutionary game theory, which is a little bit difficult because I assume most of you actually already know the basics of evolutionary game theory. Still, it is perhaps a little bit as yesterday when we heard the basics of game theory, like Nash equilibrium. Also there, I assume that most of you probably already have heard of the Nash equilibrium, but still it's useful to put things formally down such that we are on the same page. Yeah, also just to make sure, please feel free to interrupt me and to ask questions anytime. Everything should be clear to everyone. Yeah, so as Supratim mentioned, yeah, so lately I moved to Linz. So this is a photo of Linz. It's a lovely small town at the Danube. It's really nice there. And before I really start with my talk, I wanted to give you first an impression of what has drawn me into this field. The reason why I'm doing evolutionary game theory is because I believe it's awesome. And I believe it's awesome because I had the best course in the world on evolutionary game theory, which happened to be by Carl Sigmund. And what made me fall in love with this subject is just how many different mathematical techniques you might use, like from linear algebra or dynamical systems or probability theory, all this kind of stuff, but also the nice applications that you have. And so I wanted to introduce 3 applications, and you might know most of them, but still it's nice to see them. So one is this famous example of mating behavior in male lizards. So there is this lizard species out there where the males come in 3 different kinds. And it's actually really easy to distinguish them because they have different throat colors. Like some of these male lizards have orange throat color, so that would be this one. Some of them are yellow, and some of them have a bluish throat color, so this would be the one in the middle. And what is interesting about them is they do not only differ in their throat color, which makes them easy to distinguish, they also differ in their mating behavior. So usually males with orange throats, they are very aggressive, and they would try to have a very large territory, and what comes with large territory is like access to many females. And the male with blue throats, they're a little bit less aggressive, so they also wouldn't have many females, perhaps they would only have one. And the males with the yellow throats, they don't have a territory at all. In fact, they look a little bit like females themselves, so they are very easy to confuse with females. And as a result, they would usually sneak around, and whenever there is a mating opportunity, they would just use it. And I mean, that's just a very interesting observation. And one question that you might have about the system is, why would we even see this coexistence of different behaviors? Like, naively, if you think about evolutionary theory, you might think that, okay, one of these 3 strategies must be the best strategy. And then, I mean, evolutionary theory would say survival of the fittest. So one of these, in the long run, one of these male strategies should succeed, and the other 2 should go extinct. So what is going on here? Okay, so another example is cooperation and punishment in humans. And there is this really famous experiment by Ernst Fehr and Simon Gechter. The way how this experiment works is as follows. So you would have groups of 4 individuals, and each of these individuals gets some initial endowment. Like here you could think everyone gets 10 euros. Then you get to choose how much of these 10 euros do you keep for yourself and how much do you contribute to a public good. The rules are such that whatever you give to the public good, it's doubled and then evenly distributed among all group members. So for every euro that I give to the public good, it becomes 2 euros, and then 50 cents are given to all other group members, including me actually. But for every euro I give, I only get 50 cents back. But obviously every euro is transformed into 2 euros, so it's the efficient way to actually give. Just if I'm selfish, I actually hope that everyone else gives, and I don't give at all. And like what I usually think about here is like teamwork in groups. Like if you get an assignment in school, this is often how it works. Like you really want that everyone works together and that you get the project done, but you always hope that someone else is doing it, and usually you always have some free rider in your group. Now what is interesting, like if you play this game just as such, usually what you see is that cooperation breaks down after a while. But what Fehr and Gechter did is, like after each round, there's actually a punishment opportunity. And how this punishment opportunity works is I pay 1 euro, in order to reduce Sylvia's, for example, endowment by €3. I guess on one of the posters yesterday, I've seen this as spite, and perhaps it is a form of spite because it's so obviously useless because I reduce money, I burn money literally, it costs me €1, it costs the other person €3. It seems inefficient. And still, if you do this, you see without any punishment, cooperation goes down, and as soon as you add this punishment option, cooperation goes up. And you might think, okay, of course, if I know that other people can punish me, then I'm more cooperative. There's nothing surprising about it. But what was special about this experimental treatment is that groups were reshuffled after every round. So you wouldn't meet the same person again in future. And if I know I never meet you again in future, why would I even punish you? So there's actually no incentive to punish each other in this kind of game. And knowing that no one has an incentive to punish me, I could think, okay, no one will punish, so therefore I don't need to cooperate, but actually the opposite happens. I should make one more statement. What you see here was done in Zurich, and what you see here is also typical for Western countries. If you, the same kind of experiment has been repeated in other countries, and in some countries, you see that punishment is just misused and everyone punishes each other. Yes? Sorry? This is just an illustration. So what happens in an experiment, you could change your behavior in every round. Yeah. And also here the question is, okay, how can we make sense out of these behaviors? Now, the last example that I would like to give is signaling games. And the idea here is that sometimes you invest into something that has no direct value. And one example, for example, is getting an academic degree in something that you're not actually planning to work on later on. For example, I could imagine that most of you perhaps stay in academia, but some of you might actually go to industry in the long run. And it's very well possible that in the long run, you need none of your skills, perhaps, that you actually learned and trained very hard while you were a PhD. And still, it actually makes a lot of sense to do a PhD. And the question is, why? And I mean, another example that is very famous is this peacock's tail that is just huge. It doesn't give you any benefit in flying. Rather, it actually hinders you when flying. So also here the question is, why would you actually invest in having such a huge tail? And you can make an argument that you do this because it's a useful signal. But then the question becomes, is a signal for what exactly? And what are optimal, given that you want to signal something, what are the optimal kinds of signals that you could send? So also here, there are very interesting questions that come up here. And so examples like these have drawn me into game theory. Because what do all of these examples have in common? There are individuals, and these individuals can either choose between different behaviors, or they can just have different behaviors, without choosing them. And what is optimal for each individual actually depends on what other people do. And obviously the appropriate framework, whenever you have these two things, is game theory. Now, what is actually crucial in what follows is that not in all examples that I've given to you, it was important that people made conscious decisions of what they do. Even if you decide subconsciously whether to cooperate or not, still game theory might apply. And obviously, the lizards, they don't make a conscious decision which throat color they want to have, and as a result, which behavior they would do. Obviously, this is not consciously chosen. It evolves somehow. And so that's what evolutionary game theory is about. All right, before I can really start with the actual talk, let me give you an overview of what all my talks will be about. So today is this introduction to evolutionary game theory. Tomorrow I happen to have two talks. One will be on evolution of cooperation. We heard a little bit of that yesterday, particularly about direct reciprocity, cooperation in repeated games. The other talk will then be about the evolution of social norms. Also social norms is something that can evolve and that can propagate perhaps, and indirect reciprocity. And then in first day's class, I will tell you a little bit more about my own research. There might be a little bit of my own research also in the previous talks. Okay, that's that. Before I go into evolutionary game theory, just to remind you a little bit, like what we actually heard yesterday, just that everyone is on the same page. Like, what is a normal form game? Like, a normal form game is a game between two players. They can choose between a finite number of actions. That's what I assume here. They move simultaneously, and they know all aspects of the game. The only thing that they don't know is what will the co-player do. And usually how you represent such games is like with this payoff matrix or payoff by matrix, where usually the first entry is the entry of the payoff of the row player. The second entry is the payoff of the column player. All right. Then another definition that we heard yesterday is the definition of dominated strategies. So a dominated strategy is a strategy that is just obviously stupid. Like in the sense that there is this other strategy, and no matter what the other co-player will do, you would always get a better payoff with this other strategy. So if you would like to make a minimum requirement of what rationality means, is it should require not to use strictly dominated strategies, because they are just so obviously stupid. Like, you do not even need to form beliefs about your opponent. It's just obvious that they are never good, okay? So the other definition that we heard yesterday is the definition of a Nash equilibrium. So this is just a stable state. So given that we are already in this Nash equilibrium, I do not have an incentive to deviate. So, like, I cannot improve my payoff, but also my co-player cannot improve her or his payoff. Now, if you look at these definitions, they seem to make rather strong requirements on the cognitive abilities of individuals. Like, okay, for dominated strategies, what is it that you need to know? You only need to know your payoff, and you need to be able to analyze your payoffs. I mean, that's not too much of cognitive effort, I would say. But like, also what we heard yesterday is this iterated elimination of dominated strategies. So I know that you would never play this strategy, and as a result, for me, it's never worth to play this strategy, and so on. For that, it's not enough that I understand my payoffs. I also need to understand your payoffs, and I need to know that you are rational, that you can do this kind of reasoning. And actually, for really iterated elimination of dominated strategies, I would also need to know that I know that you, and this kind of like common knowledge of rationality. And that's actually quite, if you look at it, quite a strong assumption that you make on individuals. And I guess the subject of this talk is to convince you that you do not actually need to make almost any assumption on cognitive abilities. Okay, and the example that I would like to start with is also like the first example that was actually proposed in evolutionary game theory. So this is by Maynard Smith. And the example is about a conflict among deer. And the way how it works is like, if you observe deer, they often engage in ritual fighting. And what that means is that if two male deers meet each other, they have these big antlers, they could really hurt each other. But what they usually do is first they walk in parallel, and then they face each other, and only once they face each other, they really start fighting. And you might ask yourself, okay, why is there this ritual? Why, while I'm walking in parallel to my opponent, why wouldn't I just do this and hurt my opponent really badly? Like before Maynard Smith, the theory was, well, deer don't do this because it's bad for the species. Like if deer would do this, like it will really reduce the fitness of the whole species, and somehow deer magically figure this out, and therefore they don't do this. And now what Maynard Smith suggested is like a simple, what we would now call a game theory model. So suppose there are two types of individuals, and they differ in whether they choose to escalate a fight. And the nice types you call doves, and the ones who escalate the fight you call hawks. And now I need, so as always when I define a game, I need to define three things. I need to define who are the players, so in this case the two deer. I need to define what is it that they can do, so in this case escalate or don't escalate, or hawk and dove. And I need to define what are the payoffs. So in this case, I assume that if I win the contest, I get a benefit B, but if I get insured, I have a cost of C. We assume that the cost here is actually higher than the benefit. And we assume that if we both, and just let X denote the fraction of hawks in the population. And we assume that like if we both fight, we are equally strong, so then there's a half-half chance of winning this fight. All right, so we can now actually calculate what is the expected fitness of the two types. Now, suppose you are a hawk. Then with probability X, you meet another hawk. And then either you win or you lose. If you win, you get a benefit, B. If you lose, you get a cost of minus C. And because you're equally strong than the other hawk, there is a probability of 2 for each, okay? Now, if you meet a dove, you will try to escalate, the dove will run away. So if you meet a dove, actually you will get the benefit for sure. So this is the payoff function of hawk. It obviously depends on the fraction of hawks in the population. Okay, and similarly, we can actually derive the fitness of a dove. Like if a dove meets a hawk, it runs away, it gets nothing. But if a dove meets another dove, well, they do their ritual fighting, nothing bad will happen, and with probability 1/2, they get the benefit. Now you can calculate what is the fitness difference between those two. So what is the difference of, between the fitness of the hawk minus the fitness of the dove? And you see, well, simple algebra tells you that it's 1/2 B minus CX. Now, in particular, like if X was 0, there are no hawks in the population, you would see that the fitness difference is 1/2 over B, which is positive. So if there's no hawk at all in the population, like one single hawk would actually have a positive fitness, a higher fitness than the resident doves. And conversely, like if everyone is a hawk, like if X is 1, you would have here B minus C, and because C is larger than B, this would be negative. So if everyone is already a hawk, this fitness difference would actually be negative, so doves would actually have a higher fitness. So what you would expect to happen, like now very hand-waving, you would expect to happen that if X is very small, like hawks would invade, and if X is very large, if X is very large, then doves would invade. So you would actually expect some dynamics like this. So at some point in the middle, they would probably meet. Like at some point, they would have the same fitness. Like actually for these parameter values, you can actually calculate where they have the same fitness. It's exactly if the fraction of hawks is B over C. And so you would expect, like naively from an evolutionary process, you would expect that there are some forces that push you towards this point. Okay. So this is kind of a naive evolutionary perspective. What is interesting here, by the way, is that the larger the cost of serious injuries, so the larger the C, the closer this fixed point will be to only doves. And so in particular, like if you think of deers with very heavy antlers, like there's a huge cost of escalating, and therefore this would explain why actually most of the deer play a dovish strategies. All right, so this is the naive evolutionary approach. You could think now, okay, like I understood now this naive evolutionary approach, like how does it actually compare to the classical static approach of doing game theory? And so it's the same game. I wrote again now the payoff matrix. Yeah, so what you note from it's a very special payoff matrix. It's symmetric. So it has this property that like if the green matrix is matrix A and the blue matrix is matrix B, then A transpose is B. So it just means that we are essentially the same. Like whatever you could get in principle, I can get in principle. Whatever you can do in principle, I can do in principle. And for these symmetric games, we usually drop the second component. So we only write the payoff of the role player. Now what you can do here is, like you can, of course, compute the Nash equilibrium. And it turns out there is only one symmetric Nash equilibrium. And the symmetric Nash equilibrium actually is to randomize between playing hawk and dove. And the probability with which you would play hawk is this one. It's B over C. And I guess this is a familiar expression. We just saw it before. That's also what we convinced ourselves the population should converge to in the long run. So there seems to be some close connection between Nash equilibrium and the evolutionary approach. And to make this a little bit more formal, I would like now to introduce things a little bit more rigorously. So like now consider an infinitely large population. And And like these individuals in this population can choose among n actions, say. Let's just say that a proportion of x1 chooses action 1, and a proportion of x2 chooses action 2, and so on. Now, we assume that these individuals meet each other randomly, and whenever I'm an I-type, the other is a J-type, I get a payoff of Aij. All right, and then because players meet each other randomly, I can actually compute my expected payoff. Because if I'm an I-type, like with probability x1, I meet a 1-type, so I get AI1 times x1, and so on. I just sum up over all the possibilities, and that's then my expected fitness. And also it's useful to compute what is the average fitness in the whole population. Well, it's a very similar thing, like you just take every type's fitness and you weight it by how many of those types are there, and then you sum up. So this is the average fitness. And this brings me to the probably most well-known object in evolutionary game theory, which is the replicator equation. So the replicator equation is just a very simple model of how strategies might change in time, like the proportion of players who play each strategy. And it just says that, well, if my strategy performs better than average, the proportion of strategies will increase. Otherwise, it will decrease. All right. Now, okay, like it's easy to write down these kinds of equations, like, but obviously these kinds of equations only make sense if they have certain properties. Like, for example, the first property that you might want to have is, like, I mean, you might interpret this differential equation as an equation on whole Rn, but this wouldn't make much of sense because, like, I just told you that the interpretation of these xi is a probability distribution, like here, the proportion of those players who play strategy 1 and the proportion of those players who play strategy 2, and so on. So what you would actually like the strategy to satisfy is that if your initial population is a probability distribution, then also in the long run, the result of this equation will be a probability distribution. Otherwise, this equation doesn't make a whole lot of sense. And actually, that's what this first result here says. Like if I start with a probability distribution, I will get a probability distribution at all times. So that's actually a minimum requirement on any reasonable ODE that you might want to describe probability distributions. Also, one property is that the boundary phases are invariant. So if a strategy is not there in the beginning, it will never be introduced. And that's actually quite obvious from this definition, because like here there is an xi on the right-hand side. So if this is 0, the slope will always be 0. Yeah, and the last property, I like it because it makes this nice connection to classical game theory. It's that dominated traits go extinct. And like, I didn't even tell you where this replicator dynamics comes from, but it could be a very simple birth-death process. So individuals do not even need to be aware that they play a game. They do not even need to be aware that there are different traits or whatever. Like, if replicator dynamics is the result that some individuals have more offspring than others, then dominated strategies would go extinct. And even more than that, even strategies that wouldn't survive iterated elimination of dominated strategies, also they would go extinct. So it's kind of like, even when the individuals themselves are not smart, the evolutionary process makes them smart in the long run. Yeah, one could go on and prove these things, but I guess I won't. The thing is, it's actually fairly simple. So it's 1 or 2 lines to prove these things. Yeah. Another thing that will be now important soon is that how do we actually represent the state space here? So as I told you before, like you could interpret replicator dynamics on the space of Rn, but that wouldn't make a lot of sense. Like you should look at the space of probability distributions. And so, for example, if there are 2 strategies, so this is actually the proportion of players who play strategy 1. This is the proportion of players who play strategy 2. So you could be here at 1, 0, for example. This would mean that everyone plays strategy 1. Could be here at 0, 1. This would mean that everyone plays strategy 2. So the relevant space that we are talking about is actually this. So the sum of these two quantities need to sum up to 1. And obviously, you could always look at this space now in R2, but what people usually do is they just take this line and they look at the dynamics along this line. Okay? So this would be, for example, all 1. This would be all 2. Okay? And now, similarly, what you would now do for for 3 strategies, so it would look like this. You would have these triangles. And usually people, when they illustrate replicator dynamics, they don't bother illustrating things in 3D. They would usually just show this triangle. Okay? And the same you could do actually for 4 dimensions. Now it's not even possible to draw this, but it's still possible to actually draw this kind of representation. So it's this tetrahedron. Okay. Yeah, I just explained this such that you can understand some of my future pictures. So this is what I just shown you. Actually, like you could look at R2, but what we instead do is actually look at the line. And actually, implicitly, I've already done this. Like when I talked about the hawk-dove game, I actually already restricted things to a line. And yeah, the same here, and the same here. Okay. Yeah, and so now we would like to get a little bit a feeling of what is replicator dynamics about. And as often when you want to get a feeling of an object, the thing that you should start with is the simplest non-trivial case. The simplest non-trivial case is the case of 2 strategies. So in this case, like suppose there are 2 players, there are 2 strategies, so you can work with a 2x2 matrix. And then you can ask yourself, okay, for these simple 2x2 games, how does replicator dynamics look like? Like what are the possible cases that can even occur? So we can actually represent now replicator dynamics as a 1-dimensional system, as I just explained. We can say X is the proportion of those players with action 1. 1 minus X is the proportion of players with action 2. And then we can actually compute what are the fitnesses of each player. So for example, if I'm a 1 type, like with probability X, I meet another 1 type, then I get payoff A. With probability 1 minus X, I meet a 2 type, then I get a payoff of B, and so on. And now we can actually do the autopilot. So these are our fitness values. We can just plug them into the equation of the replicator equation. So this is what we do. So, so we say X dot is X and my fitness minus the average fitness. Then you can do some simplifications. Like I can actually plug in what is the average fitness. Well, it's X times my fitness plus 1 minus X, the co-player's fitness. And then you can simplify a few things, and what you get is this expression. So it's actually a polynomial of degree 3 in X. And what is clear is that X equals 0 is always a fixed point. So if no one is there playing strategy 1, then it will stay like that. Also, X equals 1 is always a fixed point. The question is, what happens in between? And what happens in between depends now on this linear function. So there are 2 kinds of fixed points, like one is the corners, and possibly there is another fixed point in the interior, like you can always compute this, but then you need to check, is this actually in 0, 1? Like it could be outside of the unit interval. All right, so this is the general theory. Now let's look at a few examples. So the first example is this hawk-dove game that we always looked at, now with specific payoff values. So if you just plug now these payoff values into the formula that I gave you before, what you get is X. So on the right-hand side, you get X times 1 minus X times 1 minus 2X. And again, what you see is like if X is 0, this expression is positive, so you would expect X to grow. But if X is 1, for example, this thing becomes negative, so you would expect X to decrease. And if you now draw the phase portrait, what you see is that there are these orbits and they go to this fixed point, which is exactly in the middle in this case, at X equals 1/2. So what you see here is what this case is sometimes called, it's stable coexistence. Like there are two different actions, and in the globally stable equilibrium, those two strategies would coexist. All right, another example is this stack hunt game, I guess, which we also had already. So this is an example of a coordination game. Again, we can just do the autopilot. We can plug these payoff values into our formulas. What we would get in this case is this formula, so this differential equation. What you would see here is that if x is 0, this is negative. So x would not even invade, like this first strategy would not even invade. If x is 1, this is positive, so it would even increase further if it could. So if you draw now the phase portrait, it looks like this. So there are actually two stable fixed points at the corners. Both are locally stable. Then there is this interior fixed point, which separates the two basins of attraction. So this is the basin of attraction. Like if your population, for example, starts exactly in the middle, like if in the beginning 50% are hare and 50% go for stag, then you would go for hare. We heard this yesterday because hare is risk dominant. And if you assume that in the beginning at least 70% of the population go hunting stag, then there would be a dynamics towards stag. So we call this bistability because there are two stable fixed points. Now, the third example is the prisoner's dilemma. So here the payoffs are like this. Again, we can do autopilot. We can just plug these values into a replicator equation. We see that this object on the right-hand side is never positive. So the proportion of cooperators would always either decrease or stop. So this is actually how the phase portrait looks like. Like if you start in the interior of the state space, for sure the cooperators would go extinct. Now for the experts here, are these all cases? Is there anything else that can happen? Yeah.
If you did repeat interactions of the same, like your strategy basically, if you had someone do the same business dilemma again, and if they were someone who would dissect, then if you do that again, you're going to lose out because overall your payoff, you're more likely to live if everybody cooperates. So you're going to select in the population for, well, not cooperators necessarily, but like someone who cooperates sometimes.
That's right. Yeah, great. Yeah, great comment. So if I understood you correctly, you would argue, okay, like, for example, in this business dilemma, if you do it only once, this is indeed what happens. But why only play it once? Like, you could play it repeatedly, then you might get a completely different dynamics. And that's completely correct. And I will talk about this tomorrow. Today, we only talk about non-repeated games. Still, you might think, are these all possible like dynamics that you could see? And now, if you think that I'm rational and there is still some space, so obviously I left some space down there, and you think I'm rational, then perhaps there is even another case. And there is another case. It just happens that it's boring. So this is the last remaining case. And in this case, your payoffs really don't depend on what you do. Like, no matter whether you play action 1 or action 2, like it depends on what the co-player does, but it doesn't depend on what you do. And in this case, this would be how it looks like. Like everything would be a fixed point. Okay. This case is sometimes called neutrality. And qualitatively, these 4 cases are everything that can happen with replicator dynamics for these simple kind of normal form games. Yeah, so in particular, no chaos can happen or no cyclic orbits can happen, but obviously you expected that because things are on a line. So on a line, it's hard to have orbits, cyclic orbits and all this kind of stuff.
So you are including harmonic game in the business dilemma?
Yes, yeah, that's right. I mean that would be another case. Like there's another case of dominance where actually everyone becomes a corporate in the end. Yeah. All right, so these are the simple 2x2 games, and by now we have understood them. So these are the 4 cases that can happen. Now, if you want to understand the dynamics, of course, like you understood the simplest case, then you ask yourself, okay, can I understand the next complicated case? And obviously, there is actually a paper that analyzes in all 3x3 games. I believe there's something like 100 possible cases. And obviously we won't do this, but still it might actually be useful to see, like from a payoff, I give you a payoff matrix and you need to tell me what happens. And so we will play this little game, and we will play it with what I call the volunteer's timing dilemma. So some of you might already know the volunteer's dilemma. So the volunteer's dilemma is the following task. Like you might actually think of two friends who live in the same house. There are dirty dishes in the kitchen sink. You hate dirty dishes. You would really like that these dishes are washed. In the worst case, you would even do it yourself. But even better, you would like it if the other one would do it. Okay? So this is the volunteer's dilemma. It's not exactly as the prisoner's dilemma, because the prisoner's dilemma you would always like to defect. But in the volunteer's dilemma, if I already know that you won't wash the dishes, I would like to wash the dishes. Okay? And now I make it, this would actually be a 2x2 game, because like I can volunteer or not volunteer. Now I want to make this into a 3x3 game, and therefore I introduce timing to this game. And the way how it works is as follows. Like, I don't only have the chance to think about, would I like to volunteer or not volunteer? I can also think about, would I like to do it now or wait a little bit? And suppose we live in a world in which there are two possible time periods, so I can either do it now or tomorrow, but I really wouldn't like to wait for any longer. And so the rules here are now that if someone volunteers early, everyone gets a benefit of 5, because everyone is really happy that the kitchen is clean. If no one volunteers early, but someone volunteers late, still people get a benefit of 4. Like they really hate that for one more day they live in a dirty kitchen, but they are happy that at least on day 2 things are clean. And the rules are such that volunteering comes with a cost of 3. And here we distinguish between 3 strategies, like a cooperator would just clean immediately. A defector would just never clean. And now the strategy wait and see is, yeah, I don't clean on the first day, and if you clean, I'm happy. But if you haven't cleaned on the first day, I will clean on the second day. And yeah, if you now plug in these payoff values, this is actually how the payoff matrix looks like. Now it requires some advanced skills to stare at this payoff matrix and to tell me how replicator dynamics for this game would look like. So does anyone have an idea how replicator dynamics would look like? Or can anyone even tell me how we would now start analyzing this game? Yeah, so let's do it together. So obviously we are here in this case. There are 3 strategies. So the object that we will be playing with happens on a triangle. Okay. So we are living on this space. So this point here would be everyone cooperates. This point here would be everyone defects. This point would be everyone plays wait and see. Now, usually how this is done is, before you even start with the whole game, like you look at the restricted game, like you look at the boundaries here. Like suppose there are no defectors, what happens between cooperators and wait and see? So you kind of ignore here the 3rd row and the 3rd column, and you only look at this submatrix. Now this is easy because this now is a 2x2 game. We already know how to analyze 2x2 games, like we already have developed a formula for that. We can analyze this. So in particular, like if you only look at this 2x2 game here, you could see that if my co-player cooperates, I would rather not cooperate. So therefore, a pure cooperation population cannot be stable. But also, if everyone plays wait and see, I would rather not play wait and see. So therefore, a pure wait and see population is also not stable. So what you would see here is a dynamics inwards. And now, if you would actually calculate the 2x2 replicator dynamics, which we've already done before, you could even compute the fixed point. So obviously, for topological reasons, there must be a fixed point somewhere in here. And we would be able to compute the exact location of this fixed point. Suppose it's here. Does everyone understand so far, or should I make this computation explicit? So what you would actually do is you just compute the expected payoff of a cooperator, which is always 2, and you would compute the expected payoff of wait and see, which is, say, 5 times x plus 1 times 1 minus x. And then this is a system of linear equations. You set those two payoffs equal, and then you get a solution in X. Okay, so this is how you analyze the subsystem between cooperation and wait and see. Now, of course, you could do the same thing with the other two subsystems. What you would see is that it's always the same dynamics. Like it's always the case that wait and see, if it competes with the factors, it wouldn't be stable. So also here you have some fixed point in the interior. Also here you have some fixed point in the interior. Okay, so now you understand the dynamics on the boundary. Now you might ask yourself, okay, like these fixed points, are they actually stable? Like if I start here close by, if I introduce a minority of defectors, would this minority of defectors invade or would it go extinct? And if you do the calculations here, like you can actually, if you know the fixed point here, you can actually compute what is the payoff in this fixed point. In this case, it happens to be 2 because cooperators always have a payoff of 2. You could calculate what is the payoff of a rare defector in this fixed point. If you do the math, you would actually see that a rare defector gets a slightly higher payoff. So here, you go inwards. And you can do the same thing with the other two fixed points. You go inwards. Okay? So this is this, another step. And the last step that you could do is like, you could ask yourself, is there actually a fixed point in the interior? So what would need to be true in the interior, like you always have these equations that, so replicator dynamics looks like this, Fi minus F bar. So if you have a fixed point in the interior, it must be true that every strategy gets the same as the average payoff. But because the average payoff is actually a weighted average of all individual payoffs, it must actually be true that the fitness of cooperators is the same as the fitness of defectors, is the same as the fitness of wait and see. So this gives you two equalities, and in addition you have this equality xc plus xb plus xw equals 1. So overall you have some linear equalities. You can use this to compute whether there is an interior fixed point. You would see that there is actually in fact an interior fixed point. Also, like the usual tricks from dynamical systems you could use to see whether this fixed point is locally stable. You would see, yes, this fixed point is locally stable. So you would get a pretty good idea of the replicator dynamics of the system. Now, the last step after you've done these analytical things is like, so this is just summarizing what I explained. So first you do the dynamics at the edges, then you look for a fixed point in the interior. Then you do some local stability analysis for these fixed points. So this is what you can easily do mathematically. And in the end, what people often do is like they draw some sample solutions. And in this case, these sample solutions look like this. Like we already know, this fixed point, for example, is unstable. It will move to the interior. So here you actually see that this interior fixed point is globally stable. And this is roughly how the orbits look like. So this is actually how you can analyze any 3x3 replicator dynamics. All right, yeah, I will save you from analyzing 4x4 games because I guess by now it's a bit boring, but you get the trick, okay? Yes? Yeah, that's right, that's right. It's a kind of a hidden version of the war of attrition. So the war of attrition, for those who don't know, is exactly this kind of game where you try to wait longer than the opponent. Because there's something that needs to be done that neither of us wants to do, and I try to wait longer than the opponent. Sorry, say that again. Yeah. That's right, yeah, you would do it again like as follows. First you do n equals 2, then you do all the subplanes, then you try to do the interior, and at some point you probably do numerically solving some orbits. Yeah. All right. Yeah, in the end, in this game, all strategies coexist, which probably wasn't that easy to see if you just stare at the matrix itself. Yeah, the average fitness in this equilibrium happens to be 2, which is kind of obvious because in this equilibrium, everyone needs to get the same payoff, and cooperators just always get the payoff of 2. Yeah, so this was one example. Without doing any calculations, let me give you another example, which is this well-known rock, paper, scissors game with this kind of generalized payoff matrix. So the rules are as you are used to it. The payoff matrix is now a little bit more general. And now the question is, okay, like if I now stare at this payoff matrix, what will be the orbits? And it turns out, actually, just this payoff matrix alone won't be able to tell you the orbits, because it also here depends on the exact magnitudes of this B1s, B2s, B3s, and A2s. It depends, it turns out that there are three possible kinds of dynamics. If it just so happens that the product of the A's is the same as the product of the B's, you will have closed orbits. So in particular, for the standard rock, scissors, paper game, where if you win, you get 1, and I lose 1, you would get closed orbits. Another way, perhaps a more elegant way of saying this is, if the determinant of the above matrix happens to be 0, you get closed orbits. So this is another case. If the product of the A's is smaller than the product of the B's, you get actually orbits spiraling to the interior solution. And you see the opposite effect if the product of the A's is larger than the product of the B's. You see orbits moving away from the interior solution. So these are the three possible cases that can happen in a rock, scissors, paper game. And now we are actually prepared to revisit one of our examples. We can actually look at this mating behavior in lizards. Because it turns out that the game between these lizards is exactly described by a rock, scissors, paper game. Namely, like these are the three types that I've explained to you. And now, if you think about it, like if there are a lot of males that have large territories, it is actually a very profitable strategy, because these males cannot be everywhere. It's a very profitable strategy to just sneak around, and whenever there's opportunity, you use it. But if there are a lot of these sneakers around, suddenly it pays off to have this small territory that you just defend. And once there are a lot of these males that just have these small territories, like no one prevents you from increasing your territory. So there is this kind of non-transitive ordering between these three strategies. And now, actually, if you collect the data, like you might ask yourself, okay, like I know in the rock, scissors, paper game there can be three possible dynamics. Either there can be these closed circles, or it can converge somewhere, or it can move towards the boundary. If you here collect the data, like what the researchers have found is that this is actually one of the cases where in the long run, the dynamics seems to settle at some equilibrium. Okay. So you see some cyclic behavior, but it's not that these cycles become bigger and bigger, for example. Now there is actually another famous example of rock, scissors, paper. It's in this bacteria E. coli. And there are actually 3 strains of this E. coli, like just the plain vanilla strain of E. coli, but also the strain of E. coli that actually produces some toxin that actually kills everyone around, but actually also has an antitoxin itself. And there is this, so there is this third strain that doesn't even produce the toxin, but that has the antitoxin, so it's resistant. And also here, you can ask yourself, okay, what is the overall dynamics? So it just so happens, if there are only normal bacteria around, you have an incentive to produce the toxin and the antitoxin, because then you can kill everyone else. But if there are a lot of those toxin producers around you, like you don't need to produce a toxin anymore. It's there anyway. Like you can save the metabolic cost and just produce the antitoxin. Like if there are a lot of individuals who just produce the antitoxin, like you don't need the antitoxin anymore. You can just become the plain vanilla bacterium. And so also this has this non-transitive dynamics. What you see here is that in these kinds of experiments, like in a mixed plate, so this is kind of the experimenter's analog of a well-mixed population, like you don't allow the formation of colonies and this kind of stuff, but rather you mix the plate. What you would see is that in the long run, 2 strategies go extinct and only 1 survives. So this is kind of the rock, scissors, paper dynamics, where you go to the boundary of the state space, and at some point there will be a stochastic extinction event. Okay. Yeah. So these are the examples that I wanted to talk about. Like now I have a few more comments more generally about replicator dynamics. So the first is, like I already suggested a little bit, that there are these connections between replicator dynamics and static game theory, which I find really beautiful. Like so far, I've just given you these small examples and I hinted at things, but it's actually not a coincidence that there is this close relationship between replicator dynamics and like, for example, Nash equilibrium. In fact, you can prove the following thing, not only for 2 dimensions, but arbitrary dimensions. The first thing is, like, if you have a Nash equilibrium, that Nash equilibrium is a fixed point of replicator dynamics. Another property is, like, if you start in the interior and you have some orbit that converges, the thing that it converges to, it must be Nash equilibrium. And the third thing is, like, if you have this fixed point that is Lyapunov stable, this fixed point must be a Nash equilibrium. So there is a really strong connection between Nash equilibrium and replicator dynamics. So this is sometimes called the fork theorem of evolutionary games. So there's really this nice and beautiful connection between static game theory and evolutionary game theory. That's also part of the reason why economists like evolutionary game theory, because it gives a nice justification for concepts like Nash equilibrium without having to require that people are super rational, or, for example, that they are in a group where I need to know everyone else's payoffs. If things are inherited and it's just a birth-death process, for example, you don't need to know anything. Like, actually, evolution does the job. All right. And then one more remark. Okay, so what is the status of replicator dynamics overall? So what do people think of it? And I don't know people. I know what I myself think about it, so that's what I will tell you about. Like, for me, it's one of the standard models. Like, whenever you have a game, like, and you want to know what could I do with it, like, one approach that you could do is, well, try replicator dynamics. And like, what is the reason for that? Like, historically, it's just one of the first examples, especially in this more biological world of a dynamics that looks at evolutionary game theory. The second reason is that, I mean, it's a fairly simple equation and it's well understood. Like, people understand what's going on with replicator dynamics. The third very nice thing is that there are actually beautiful connections between replicator equation, which is one of the main equations in evolutionary game theory, the Lotka-Volterra equations, which is one of the main equations in population ecology. In fact, in a very well-defined sense, they are equivalent. So one can make an argument that they are exactly the same thing. So the person who first realized this is Josef Hofbauer. So Josef Hofbauer has a paper in which he exactly proves that replicator dynamics in very specific sense is equivalent to Lotka-Volterra. And the fourth thing is, as I already explained before, there are these many beautiful connections between replicator dynamics and classical game theory. And like, even without making any assumptions on the rationality of players. And again, it's useful to pause a little bit and to wonder, how is this even possible? Like, Nash equilibrium seems to be so restrictive, and it seems to require so many things. Here you get it for free. And by the way, you might think, okay, like, replicator dynamics can do this. So obviously this is probably most of the dynamics do this. Like, if you would write a slightly different ODE, probably you would get similar results. It turns out, and this is another cool result by Josef Hofbauer, that in a very specific sense, replicator dynamics is special, because what I told you in the beginning is that replicator dynamics leads to the extinction of iteratively dominated strategies. So this is actually a property you would like to have, because you would believe if there's a population, there's this obviously bad strategy, it would go extinct, and then there's the second bad strategy, then this would go extinct, and so on. So you would think that any reasonable kinds of dynamics has this kind of property. It turns out that for almost all, now in a mathematical sense, for almost all dynamics, like almost all dynamical equations that you could come up with, this property does not hold. So for almost all possible dynamics, like what Josef Hofbauer does in this paper, he writes down 4 axioms that define what a reasonable dynamics would be. Like, for example, that it can only be a fixed point if it's a Nash equilibrium, like this kind of thing. And they show that if a dynamic satisfies those 4 axioms, almost always it'd be true that you can find a game such that there is a strategy that would be dominated, but it doesn't go extinct along an orbit of this dynamic. So in this sense, replicator dynamics is actually very special. All right.
Why are discrete versions of replicator not that possible?
I mean, that's a good question. My sense is that they are a little bit more complicated to analyze because, like, I guess if you have a three-dimensional system, for example, you cannot get chaos if you look at the ODE. But obviously, like, if you have a discrete system, already if you only have two strategies, probably you could get perhaps some chaos. And just like the toolbox of, people like the toolbox of ODEs, I guess. But yeah, I don't have any better answer to that. All right, but just to tell you, like, replicator dynamics is perhaps one of the most famous models of evolutionary game theory, but it's by far not the only one. In fact, we've heard other models already. And whether you or not you want to do replicator dynamics, it depends on your applications. For example, like, there might be properties of replicator dynamics that you don't like. For example, one property of replicator dynamics is this one that I told you before. Like, if a strategy isn't there in the beginning, it will never occur. Like, even if there's this obvious strategy that would do better than everything else, people here are too stupid to come up with the strategy. And for some applications, that might be a property that you might not like. Like, for example, you might want to introduce some mutations into this process, or you might want to introduce some limited kind of rationality that people are able to see. Like, even if the strategy is not played now, it would be a really profitable strategy, so why not try it? Yeah, and the other restriction of replicator dynamics, at least in the way that I presented it, is that it assumes well-mixed populations. So you assume everyone plays with everyone else. Also, you assume that there is a discrete number of actions. Like, this assumption of discrete number of actions is actually not necessary. Like, you could look at games with continuous traits. You could do, for example, replicator equation for continuous traits, but also what people sometimes do is using a different dynamics, which is called adaptive dynamics. So there are many other interesting dynamics out there. And just to give you a taste of what else might be out there, I present one other model of evolutionary game theory. All right, and just to have a slightly different flavor, so far we have been working with ODEs. Let's now do something without ODEs, so let's look at finite populations. All right, so what I will tell you about is called the Moran process. Also here, probably most people have already heard of the Moran process, but still, perhaps it's worth to like, walk through it. So what we do here is we consider now a population of finite size n. And what people also usually do is, I mean, obviously, you could define the Moran process for arbitrary payoff matrices, but what people most of the time do is they look at 2x2 matrices. So there's strategy 1 and strategy 2, and there are the associated payoffs. Again, you assume that populations are well mixed, so everyone is equally likely to interact. But perhaps one difference to before is, like, you cannot play against yourself. Like, you can play against everyone in the population, but not against yourself. And I guess this explains these slightly weird expressions. Like, you don't play against everyone, you only play against n-1 other players. And because you are already a player with strategy 1, you don't play against all players I with strategy 1, you only play against I-1 of them. Otherwise, this is just straightforward. Yeah, and also what people here do is they do not work directly with the payoffs, rather they work with something that is called fitness. And there are many ways how you can map payoffs to fitness. One common way is actually just to use this linear mapping. So what your payoff is this linear combination of some baseline fitness, 1 minus W, for example, and something that is proportional to your payoff. And this W is usually called strength of selection. And so this is a parameter that you can play with. So for example, if this parameter is 0, I mean, everything here disappears, then just both strategies have a fitness of 1. Here, payoffs are completely irrelevant, and you just see random drift. Now, the larger W becomes, the more important payoffs become. So people say that if W is small, you're in the limit of weak selection. If W is large, you get more and more strong selection.
So here, the payoffs are allowed to be negative as
If you allow payoffs to be negative, your W cannot be too large. Yeah, so there are natural bounds on this W. Like exactly for this reason, because sometimes payoffs are negative and you don't want to take care that your W is small enough, sometimes people use an exponential payoff to fitness mapping, because there you know that whatever the payoffs are, the fitness will be positive. Yeah. All right, and here the assumption is that evolution, like with replicator dynamics, we had continuous time, now we have discrete time. So in each discrete time step, you choose two individuals at random, like one is chosen in proportion to its fitness, and one is chosen just randomly. And the one chosen proportion to its fitness is allowed to reproduce, and the other individual chosen randomly is chosen to die. And if these are the rules, you can ask yourself, okay, like within one time step, what is the probability that the number of players with strategy 1 will move up by 1? What is the probability that the number of players with strategy 1 will go down by 1? Like obviously they cannot go up by 2 because like in each time step at most one individual changes. And these transition probabilities, you can easily compute them, like they are as follows. Like this is the probability that, like if I want strategy 1 to go up by 1, I want that one individual is chosen for birth, like this, and this is proportional to fitness, so this is the overall fitness of one individual. This is the total fitness of the population. So this is the overall likelihood that one individual is chosen for birth. And this is the probability that a two individual is chosen for death. And the same way the other way around. So this gives you the transition probabilities of the state. So what you have pretty much is like this Markov chain where you have all possible population compositions. So here, for example, would be all 1. Here would be all 2. And in each time step, you can either move up or down, or you can also happen to be the same. All right. Yeah, and okay, now, I mean, this is now a different object than it was here with replicator dynamics. So with replicator dynamics, it was all about characterizing what are the fixed points, what are the basins of attractions of the different fixed points. Like perhaps sometimes you do not even converge to fixed points and you might get cyclic orbits and this kind of stuff. So those were the kinds of questions that you were interested in infinite populations. Now in these finite populations, you might be interested in very different things. So for example, one thing that you might be interested in is what is kind of the invariant distribution. Like for example, if you also allow for rare mutations, that sometimes every once in a while, you take a different strategy, just the opposite strategy of what you're using now. What you would get here is an ergodic process, and then you could compute, like in the long run, what is the stationary distribution of this process. Yep.
So, does it make a difference if for that, if you choose randomly, there also I might be inclined to choose individuals according to their fitness, as in the individuals with less fitness should die more often than, does it help if I do it that way also?
That's right. Yeah. Yeah, so here I assume that death is just randomly, like you uniformly select individuals for death. You could make it, fitness even have a stronger effect by actually assuming that also death is somehow proportional to inverse fitness or something like that. You could totally do this. I'm actually not even sure in which kinds of games it would change the qualitative dynamics. So my sense is that probably most games, it doesn't make a strong difference. Yeah, so one thing that you could calculate now is like this invariant distribution. Like one thing that is for some reason more common to actually calculate is like strategy 1's invasion probability or fixation probability. So what is the assumption here? Like the assumption here is that in the beginning, like almost all players play 2, but now there is perhaps by a mutation, like perhaps a mutation brings you here. So now one individual plays strategy 1, all other individuals play strategy 2, and you want to know, given this is your initial state, what is the probability that in the long run, if there are no further mutations, you actually get absorbed here. And one reason why this is a very popular quantity is, as so often, because it can be computed. So for an invariant distribution, I don't think there is any simple expression in general, but for the fixation probability, you can write down a very simple expression. Yeah, and so I won't go through the details how you can actually calculate this fixation probability. I'll just tell you the beginning and leave it there. So, okay, let phi be this probability that eventually everyone adopts strategy 1, given that in the beginning only I players play this strategy. Okay, and now if you want to compute this quantity, like a very profitable way is try to come up, like it's hard to compute this quantity directly, but what is easy is to come up with a recursion for this quantity. And the recursion looks like this. Okay, like what can happen after one time step? Like it could even either happen that actually the number of players with strategy 1 moved up by 1. And after this, you ask, okay, what is the new fixation probability? Or it could have happened that in one time step, the population went down by 1. And then you could ask yourself, okay, what is the new fixation probability? Or it could have happened that actually the population, at least the composition of the population didn't change. And then you ask yourself, okay, what is the probability that you reach fixation then? And now you have this kind of recursive relationship in these fixation probabilities. Now, it's still not obvious actually how you solve this. It turns out there are a few tricks that you can make. For example, it turns out that here you have phi I on the right-hand side, and here you have phi I on the left-hand side, so this cancels. And so it turns out that you only have expressions that either have t plus or t minus. And then you can do some tricks, like you can do some redefinition of variables. Like in this case, for example, it's profitable to introduce this new variable, yi, which is this difference between these fixation probabilities. Then you can just rewrite this equation in this form. Then you can solve this for yi plus 1, so it actually has this form. And now you can actually, because yi, I mean, it just has the same form, so you actually get products of these kinds of things. So yi actually has this kind of shape. And now you can do a few further steps, like actually you now need to sum up these things in a smart way. There are two different ways how to sum up these things, then you equate these two different ways. And then you get this closed form solution. So, yeah.
Confused with this, maybe I'm thinking it wrong. So if I see this as a map, the phi I equal to pi,
yeah.
Shouldn't it be that I am in phi n minus 1 and I should multiply it with t plus, because then I'm going to get phi I in the next step?
Let me see. So I is the number of players with strategy 1. T plus is the probability that in one step, the number of players 1 move up by 1. Oh, yeah. And phi I is the probability that I reach fixation, given that in the population, there are currently I plus 1 players with strategy 1. I believe it's correct.
Okay.
Yeah.
Because I was thinking, this I see as a time step jump.
Yeah.
Then in the past, I am in phi I plus 1.
Oh, yeah.
If I reduce, then I go to phi.
Yeah, that's right. Yeah, I think it forward, I guess. Yeah. All right, so this is the expression that you get. I mean, it's a closed form expression. Like, still, perhaps, as a game theorist, you might still be disappointed because, like, I mean, you do not even see the payoffs in this kind of expression. It just looks like a very complicated expression. And if I now give you a random payoff matrix, it would be hard for you to immediately say, okay, like obviously this has a fixation probability of whatever. So what people sometimes do then to get expressions that are more explicit in the payoff values, they do look at this limit of weak selection. So remember previously I had this map that translates payoffs into fitness. And this map was just a linear map of some baseline fitness plus W times fitness. And now what you assume is that, that W becomes very small. And why would you do this? Because as often if you look at this limit that W is very small, you can do Taylor expansion. And you can stop it after linear term. So if you do this with this very complicated expression that we got for phi 1, like you just do the Taylor expansion and you stop after linear term, you get this kind of expression. So you get a term of 1 over n, and this makes sense because, like, for example, if W was 0, like if payoffs were completely inconsequential for your fitness, the probability that one single individual takes over the whole population is just 1 over n. So this explains this 1 over n. And the linear term happens to be this expression. And now you might argue this is still a rather complicated expression, but like the advantage here at least is, like here you explicitly see the entries of the payoff matrix, and you could do some analysis. Like you could ask yourself, okay, like if I now change the payoff A, what effect does this have? Okay. Now, another question that you could ask yourself is, okay, like, okay, 1 over n here is the kind of natural baseline. Like if a strategy is just as good as the resident, the fixation probability would be 1 over n. And the question is, like, when would I be better than the resident? Like, when would I have a fixation probability that is larger as 1 over n? So equivalently, you could ask yourself, when is this expression in this bracket here positive? And I mean, it's still a rather complicated expression, so you could even take another limit, like you could take the limit that n becomes really large, because then I can ignore everything that is here. What you get then is that, well, this object in here must be positive, then you would get an expression that is larger than 1 over n. So you would need that A plus 2B is larger than C plus 2D. Okay. And now, there is a very interesting, okay, like this is just a naked result, and you could take it as is. There is, again, a very interesting connection between this kind of result and replicator dynamics now. Because, like, if for this 2x2 game, you actually calculate what is the interior fixed point. For example, you have a coordination game, and you compute, there must be an interior fixed point then, compute where is this interior fixed point. And you would get this kind of expression. And what you then get is that you can tell from this position of this fixed point whether or not strategy 1 is favored by selection. Namely, the thing is, like if this fixed point, like if this area here is smaller than 1/3, this strategy is favored to invade. If this area is larger than 1/3, it's disfavored. And if you look at the phase portrait, it makes sense that this fixed point needs to be as close as possible to this point, because like in the beginning, if you are this rare mutant, you need to swim against the current. So you want this region to be as small as possible. And it just turns out under weak selection, what you need is that this fixed point is at most 1/3. All right. All right, so this is what I wanted to tell you about today. So what you should have learned is, I presented you here with 2 very basic examples of how people do evolutionary game theory in theoretical biology. So one is replicator dynamics in infinite populations, and one is the Moran process in finite populations. Like both dynamics have very interesting mathematical properties. So this actually goes back to in the very beginning why I told you that I really like evolutionary game theory, because you use so many concepts, like you use Markov chains, you use dynamical systems, you use all these tools. And also there are these very beautiful connections that you perhaps didn't see in the beginning between evolutionary game theory and classical game theory. Yeah, so this was the program for today. So tomorrow I will actually apply these methods, like I will apply, for example, evolutionary dynamics in finite populations to explore evolution of cooperation a little bit more. All right, with that, thanks for your attention. Yeah.
If one person has strategy 1, what's the probability that all others would adopt that eventually?
That's right.
So since this is as you say, pointed out, like in a Markov process and all that, So you didn't say anything how long that will take, the time
That's right.
taken.
Yeah.
So is there a possibility that there will be slowing down, something like critical slowing down at some particular point or something like that?
Yeah, it is a very good question. So the question here is, what is the fixation time? I only talked about fixation probability. What is the fixation time? How long does it take until this process actually reaches fixation? You can actually come up with very similar recursions, and then you get an explicit formula. The interesting thing is the fixation time usually depends on the game. It can depend on the game. And the answer is, like, the fixation time, like in most games, it will be something like n log n or something. But there is this game with an interior stable fixed point. There, it will actually take exponential time.
So the condition that you have shown for strategy I to be favored over other strategy for the finite population. So there you took the limit n tends to very large, infinity, right?
Yeah.
That's why the other terms cancelled.
Yeah.
So it's basically you go from finite to infinite population.
Yeah.
But still the conditions is different from what we had seen in the replicator thing, right? Because it is now a plus 2b is greater than c plus 2d.
Yeah.
But from replicator equation, it should have been, even if I just do the Nash thing, the condition should be a greater than c and b greater than d. Then a is the Nash, so it would be stable.
Yeah.
So it would be favored over the strategy b. So why the condition is not matching? Even if we are going from
so here, thank you. So here, perhaps I was a little bit sloppy in how I was explaining things. So this 1/3 rule that I was talking about, it only makes sense if there is actually an interior fixed point. So for example, it doesn't make sense, this 1/3 rule, it does make sense to talk about 1/3 rule if there's, for example, a dominated strategy. So people really only look at this 1/3 rule, for example, in a coordination game where there's a fixed point in between these stable equilibria. And there it just so happens, like if you compute just what kind of equation would the payoffs need to satisfy if this fixed point happened to be at 1/3, you would get exactly the same equation as you get now for this strategy to be favored.
Okay, so I had a question on this Sinervo rock, scissors, paper example. So you said that in order to have these cycles, you need to have a specific condition that is satisfied, and this condition is non-generic. So what do you think in terms of using this to model a real system? Because it's something that has bothered me all the time. It seems to be very unlikely that a natural system satisfies exactly a condition that is marginal.
You mean the interior condition that you would have these closed orbits?
Yeah, in order to have closed orbits, you need to have that the determinant is 0. And
that's right.
So seems unlikely for a real system.
Right. Yeah, I have the same guess as you. Probably that would never happen in a natural system. Yeah. So probably realistically you would only see 2 cases, like that you would either converge to the fixed point or that you would converge to the boundary.
Well, if you don't have other nonlinearities.
That's right. Yeah.
Thank you. So in the modern process, we took W going to 0.
Yes.
Weak selection.
That's right.
So my question is, when you do that, will that also increase the fixation time, the time required for fixation? I mean, it seems to suggest that, right?
Yeah, there I'm actually not sure. Like, I'm pretty sure that if you look at the one game where you have a stable interior fixed point, there it would actually reduce fixation time, because like what happens there, if you have strong selection, that you would always be close to this interior fixed point, and it would be really hard to move to the boundaries. So there it would actually increase fixation time. I honestly don't know what happens in the other cases.
Hello. Yeah. How easy is it to inculcate stuff like mutation, migration, and this genetic drift into replicator dynamics models as like compared to like population genetics, which is sort of able to handle the things of iterative like fitness-based evolution, but can also very easily add these more biologically relevant stuff into the mix.
Yeah, I have the sense that putting these things into replicate dynamics is a little bit easier because you don't need to care about the whole genetics side of things. For example, if I wanted to introduce mutations, like something that people sometimes do is like they have something like, I believe something like this would do the job, or let's call this mu, then you have mutation rate. So this would, for example, make sure that even if xi is 0, there would be some positive increase. And still, like I had to add this term to make sure it still lives on the unit simplex. So this would be a very easy way to introduce mutations, for example. Like there are actually more sophisticated ways of introducing mutations. For example, if you want to consider directed mutations, that from one strategy it's more likely to mutate to this type rather than to this type, then you would have to introduce a matrix here. But in principle, my sense is that, like for example, mutations or recombination, like there are versions of replicator dynamics that actually do this. That there are many stable equilibria. Yes. I mean, one example that we've seen is, for example, like this coordination game, which had this is stable, this is stable, this is unstable. And you would have this kind of dynamics. Yeah, and obviously, like the more dimensions you have, the more possibilities you have to play around here. Also, what I should say that, I mean, throughout here, we've only looked at pairwise games. You can even get more equilibria if you allow for multiplayer games. And if you are interested in this kind of stuff, you should actually talk to Chaitanya up there because he has written a very, very nice papers about that. Yeah, I mean, there are various versions of replicator dynamics that try to get at finite population things. Like, for example, you might think of population structure, like even if there's population structure, there is a kind of a replicator dynamics that captures some aspects of this population structure. But even without population structure, even if you only consider well-mixed populations, like there is some kind of replicator dynamics that you might look at. And the trick there is instead of the matrix A, you look at the matrix A tilde, which is defined as A minus A plus A transposed over, I believe, n minus 2. So you could, I mean, you might ask, where does this matrix even come from? At the moment, I just wrote it down. And you could just accept it as that. And the statement then is, like, if you take this pair of matrix instead of this one-third law would hold for all population sizes, not only in the limit as n goes to infinity. Now, what is actually the interpretation of this pair of matrix? The interpretation of this pair of matrix is that once you are in a finite population, it's not that the average payoff of the population can be anything, because you already know that your own strategy, and therefore the average population or average payoff of the population is biased in two ways. Like you know your own payoff, so this is represented by this A, but also you influence the co-player's payoff. This is represented by this A transposed. And there is some kind of derivation for this kind of payoff matrix. I mean, if you ask me, this matrix is a little bit obscure. And I'm allowed to say this because I actually came up with this payoff matrix. Yeah. Thank you.